Okay, so I think we can start this afternoon session. So we are very pleased to have Volker Melton from Harvard, who is going to tell us about translation invariance and celestial holography. Please.
Great. Well, first I'd like to thank all of the organizers for the invitation to attend this wonderful workshop and give a short talk. So please feel free to interrupt if you have any questions. So I've tried to keep this a bit informal and hopefully we'll have plenty of time for discussion. So first, we can motivate, well, why should we care about translation invariance in celestial holography? Also, let me know if anyone can't hear me and I can try to speak up louder. So first, as a review, if I start with some scattering amplitude, right, say a function of momenta, I can obtain the celestial amplitude corresponding to this by Melton, if all of the external particles are massless, by Melton transforming with respect to the external momenta. So in particular, if I parameterize my momenta by equal to some frequency omega times some unit null momenta, that is a function of z and z bar, where these are coordinates on the celestial sphere, then I can obtain the celestial amplitude by integrating each omega I of omega I to the delta I minus 1 of these. And this will define the celestial amplitude. It'll simply write as this correlation function of these external operators, where these label, say, the weight, and then like the spin, and then there's epsilon, where this particle is ingoing or outgoing. Now we know that because if I start with the scattering amplitude here, that's Lorentz invariant, the resulting celestial amplitude will transform like a correlation function of global primaries in some 2D CFT. And so we'd like to try to identify some lower dimensional system that would compute some type of amplitude that would look like this correlation function we can get out. If I start with some amplitudes, I can always plug them in this dictionary and figure out what these correlation functions should be. But in particular, these will have all of the symmetries of the bulk action. In particular, we'll have Lorentz invariance, so they'll have global conformal invariance, but they'll also be constrained by translation invariance in the bulk. Now, because translation invariance it diagonalizes this, we can see very quickly that if I have some translation generator acting on this, say, ith particle direction mu, acting on this correlation function, that this is simply going to, because I need to multiply by a factor of p inside this integral, it will simply multiply by some function of z and z bar and then shift the weight up by 1. So this is equal to epsilon I e to the d delta I and then some function of the location where I insert it. And in particular, translation invariance implies that if I sum over all of these external momenta, that this has to vanish. And so these are a new set of constraints on this celestial amplitudes. And in particular for massless particles, these are not sort of satisfied by a generic 2D CFT. For example, at 4 points, I can always use a Lorentz transformation to take any 3 null momenta and put them in a plane. And so translation invariance says that the 4th particle has to live in that plane as well. And my transform relating the bulk and the boundary correlators only integrates over the magnitude of these null momenta and not their direction. So this will sort of constrain where I can put my 4th operator. And in particular, it implies that if I have a 4-point function, say O of delta 1 to O of delta 4, this has to be some conformally covariant function of the zij's, where again, these are location on the celestial sphere, times, in particular, something that involves a delta of z minus z bar, where this is the conformal cross ratio. Now, this doesn't really look like what you'd expect from a normal 2D CFT. After all, it has like a distributional singularity and one that manifests away from points where any of the 2 operator insertions become collinear or coincident. And so it's not perhaps obvious how we should get out of this out of a 2D CFT. Even worse, at 3 points, translation invariance implies that the 3-point function of this theory has to be really distributional. In particular, it can have support only when all of the z bars are equal, or all of the z's are equal. And in particular, for the case we look at, it has to be proportional to delta z bar 1, 2, delta of z bar 1, 3, times some function of the z's that's necessary to maintain conformal invariance. And while this is a perfectly good 3-point function that satisfies all of the Ward identities for global conformal invariance, it still doesn't look like the type of correlation function we get out of some random garden variety 2D CFT that we would write down. And so this talk, I'll try to describe some ways we can actually try to obtain this distributional 3-point and higher point functions from some explicit 2D theory that is less distributional. Now, one way to try to get around this is to try to actually just change our external basis of states. After all, because of these delta functions are coming because I'm only integrating over the direction of my null momentum. Sorry, I'm not integrating over the direction of my null momentum. And so if I did some other integral transform by integrating over the z's and z bars as well as the omegas, then the result we get would be non-distributional. And you can try to do this. For example, you can take a shadow transform of some external particles, which some work by Taylor and Dunn has done, you can try to take light transforms, which are basically just a holomorphic or anti-holomorphic shadow transform in various directions. But these can be a bit dissatisfying. For one, the symmetry is still present, even if translation invariance acts in a less perhaps obvious way. And this, on its own, these translation invariants act as some complicated weight shifting operator on the 2D CFT, which is still sort of an unusual thing to have. Secondly, it sort of breaks some of the computational techniques we'd like to use. For example, with this dictionary, we want to integrate only over the magnitude of the massless particle. The coincident limit of two celestial operators becoming close together is the same as the collinear limit in the bulk. And so I can calculate a bunch of these leading terms in operator product expansions by transforming splitting functions to the celestial sphere. However, if I also integrate over all z and z bar instead of just fixing that, it's less clear that there is this nice OBE collinear limit correspondence. And while it should simply still be possible to compute such an OBE, it is less obvious how to do so. Another thing that you could try to do is you could explicitly break translation invariance in our scattering amplitude, because after all, if my scattering amplitude doesn't obey this constraint, then my celestial amplitude won't obey this constraint either. For example, one thing you could try to do is, you could take, say, if I think about Yang-Mills, I could take an action that looks like something like, the Yang-Mills action, trace S squared, and I could try to couple it to some explicit translation invariant baked background, some function 5x times trace of f plus squared, where say this is self-dual, anti-self-dual. In this case, you can actually calculate the scattering amplitudes that would come from this, and at least in the MHV sector or all plus sector, they're very simple. For example, the all plus scattering amplitude is equal to exactly some function of the total momenta, or this is the background field, or here the Fourier transform of the background field times some simple, Park-Taylor prefactor. Now we can take the Melton transform of this as well and obtain some celestial amplitude in this basis. And because I start out with something that doesn't have these momentum conserving delta functions, the amplitude I get doesn't have these momentum conserving delta functions as well. And we've seen several examples like this. We've worked out some details of the soft limits and some work along with Andy and some other collaborators. And the burn space holography story has a similar story where, because they're calculating scattering amplitudes in a background that isn't translation invariant, you end up with these smooth correlation functions. However, this does have a few downsides. First, we're working with a group that doesn't have the full symmetry group that we would ultimately like to obtain from this 2D dual. And it's also not clear how to use this to extract actual translation invariant scattering amplitudes. After all, in this theory, because I'm sort of working perturbatively in the background, and this is simply the first order term, there's also like a distributional term that occurs at 0th order in the background. And if I took this background away, this term would simply vanish and leave only the distributional term that, again, we couldn't necessarily replicate from our dual 2D CFT. And so ultimately, we'd like to find some procedure from which we can obtain these distributional or translation invariant celestial amplitudes from at least some type of 2D theory, or some type of lower dimensional theory that has, more of that looks a lot more like a 2D CFT.
I take your point on everything you said, but just from a string theory point of view, you might think it's actually quite natural to have a background for something, because if you're traditional about holography and think there might be some theory living on some defect inserted in some brains or something, that you start out in flat space and then you insert this defect, you would expect it to backreact in some way and provide a background for maybe not the graviton depending on your theory, but background for something. So I know it's not flat space holography, but asymptotically flat holography in the presence of some background might be a more natural thing to aim for, or a simpler thing to aim for and be satisfied with as a temporary step.
I certainly agree with that, and I think that's a very useful thing to do. Nevertheless, for this, I sort of want to focus on understanding how, even in principle, we could get some system with this symmetry group from a lower dimensional CFT, I would say. It's where we want to show, perhaps provide more of a proof of concept. I think there's good reason to believe that perhaps the most natural examples won't look like this. Mm-hmm. Mm-hmm. Yes. Mm-hmm. Yeah. Mm-hmm. Okay. So anyway, so for this talk, I'm going to provide some examples where we can get some translation variant system from some 2D CFT, even if perhaps it's a bit arbitrary. I guess again, you certainly expect this to be perhaps very tuned, a bit perhaps unnatural, but this is what I'm going to focus on. So the first way we could try to do is we could try to actually write these distributional amplitudes as combinations of smoother correlation functions that sort of sum up to give these delta functions. For example, we know we can write, say, a delta function of z as simply being, say, the 1 over z plus I epsilon minus 1 over z minus I epsilon. And so in particular, we can try to generalize some identity like this, write these distributional 3 or higher point functions as sums of these smoother pieces, and then try to interpret perhaps these pieces on their own as some natural thing in whatever the dual theory would be. And so this is something we may manifest in a series of papers about what we call celestial leaf amplitudes. So first, just as a brief bit of background, we're going to work in Klein space with metric ds squared equal to minus dx naught squared minus dx1 squared plus dx2 squared plus dx3 squared. Now we do this mostly for convenience. We could extend all of this to Minkowski space as well. It's just simplify some of our calculations in the middle. And so in general, we can draw the equivalent of a Penrose diagram for Klein space, and because I can sort of rotate any time-like vector into any other time-like direction, this sort of looks like half of the Minkowski Penrose diagram. Again, I have a time-like region where x squared is less than 0. I have a space-like region where x squared is greater than 0. And both of these regions are foliated by Lorentzian ADS3 mod Z slices. Right, in this region, there are signature 1, 2, and in this signature, the region signature 2, 1. Now, in particular, if I start with a scattering amplitude, is I can think of, say, writing these amplitudes as integrals over the point in the bulk where this scattering where the scattering process occurs. Right, and we're going to focus on a sort of a doubling amplitude that is an MHV amplitude, so that our momentum space amplitude we're going to work with is just going to be equal to 1, 2 to the cube. So here in Klein space, we can parameterize any null momentum by choosing 2 angles, so that p mu is equal to some frequency times q, times, So effectively, cosine sigma and sigma bar are simply going to be the angles of my 2 spinners. And omega is the overall frequency, and I define the Melton transform by integrating with respect to this omega. And in this choice of parameters, angle bracket ij is just the square root of omega I, omega j, times sine of sigma I minus sigma j. Okay. So starting from my momentum space amplitude here, and again, this will have the momentum conserving delta function of p1 plus pn. Now I can treat this MHV amplitude as a single point-like interaction in the bulk. And in particular, I can write this amplitude here as being equal to the integral of d4x, again, of my prefactor times now e to the I of x dotted into the sum of all the momenta. Right, now I can Melton transform this amplitude to get my celestial amplitude. And in particular, what we can do now is we can simply do the Melton transforms first, so that we end up with the integral of d4x of 1, 2 cubed over and 1. And now I'm going to do the Melton transform. The Melton transforms here are simply going to turn these e to the ix dot pj into a gamma of, in this case, 2h bar I divided by q dotted into x, be 2h bar j. And then in particular, because I've done the integrals of omega, these angle brackets are going to become sine cubed of sigma 1, 2 divided by sine sigma 2, 3 up to sine sigma n1. Okay, but now we can separate this integral over Klein space into an integral over x squared and an integral over each hyperbolic slice, right? So particular d4x, and these coordinates can be equal to integral over tau. Here, tau is equal to the square root of the absolute value of x squared. Then I get tau cubed from the measure, and then d3x hat, where this is now an integral over the slice where x hat squared is equal to +1 or -1. So it's integral over Lorentzian ADS3. And in particular, now my amplitude is going to be equal to, I can pull out all of the factors of tau, since all of these amplitudes here are a homogeneous function of tau. I just get tau to the -1 minus beta. Here, beta is equal to the sum of all the weights -1. And then times my MHV prefactor, sine cubed of sigma 1, 2. And now I get an integral over each ADS3. So this is where x hat squared is equal to -1 of gamma of 2h bar j. Gamma overall j is divided by qjx to the 2h bar j. Here, h bar j is the anti-holomorphic weight of the jth particle, so it's equal to delta j plus or minus 1 over 2, where it's +1 if it's a negative velocity gluon and -1 if it's a positive velocity gluon. And now this is really nice because we can recognize this as simply being an ADS3, sort of ADS3 Witten diagram integrated over this Lorentzian ADS3 slice of Klein space. And similarly, I also have to include the region where I integrate over x hat squared equals to +1 instead. But because we're in Klein space, both of these regions are sort of geometrically the same and are related by some simple parity transform. Yes.
Is there anything interesting happening on the light-like surface? That's
so here, this is gonna, the light-like surface is again sort of a measure zero set of points here, and because my wave functions aren't singular on that locus, I'm just gonna, I shouldn't contribute something non-trivial to this expansion. And in fact, we'll show this will give us the scattering amplitude.
Okay, thanks.
Question?
Well, maybe it's for the end, but I couldn't resist to ask, what if we had some kind of non-trivial dilaton profile? Like going back to your first.
So I think here, if we had, say, a non-trivial dilaton profile that was only a function of x squared, so we didn't break the Lorentz invariance, this would sort of change, that would
tau
appear,
integral.
so it would change the weighting of how these different things are combined.
But you could still do this exercise for a, like the tau integral would be more interesting, perhaps.
Yes.
Yeah, okay.
In our case, because we don't have a background, we just get this d tau of tau to the -1 minus beta. If we had a dilaton profile, there would be some function of tau here as well. But in our case, we can just do this integral and we can get that this is a delta function of beta with some normalization. And that is occurring because we haven't broken the bulk scale invariant, which forces us to have this delta beta. And I'm simply going to define the leftover part of these integrals over x hat squared equals -1 or +1 as being my leaf amplitude. So our formula ultimately is that our scattering amplitude, or our is going to be equal to a delta function of beta divided by some normalization constant times what I call the leaf amplitude L plus the the equivalent leaf amplitude integrated over the space-like region. And because we're working in Klein space and these are geometrically the same, I can, once I know this integral over the time-like region, I can simply flip all the sigma bars to minus sigma bars to find the space-like integral. So we managed to work this out in the first of our series of papers, and we explicitly showed, once we, and in particular at 3 points, because we can actually evaluate this integral over the ADS3 slice explicitly. I guess. Okay, thanks. I'll use it next. And we were able to show, in particular at 3 points, that this leaf amplitude of 1 minus, 2 minus, 3 plus is equal to some normalization constant here, which is a simple ratio of gamma functions. We get a sine cubed of sigma 1, 2 divided by sine sigma 2, 3, sine sigma 3, 1, just from the MHV prefactor, and then times some formula that look like times this cyclic permutations. And then with another term where we have to subtract the term where epsilon goes to minus epsilon in all of these terms. And so this now looks like more like a conformally covariant 3-point function because we don't have any delta functions explicitly. And it's also a single valued function of these sigma bars because of our choice of I epsilon prescription. And in particular, what we showed explicitly is that, say if I take a linear combination of this and the space-like region, we should have that our 3-point amplitude is equal to just delta beta times L plus L, where I flip all the signs of the sigma bars. When you do this, you can show that these two terms combine into some function that explicitly, through some sort of complicated delta function identity, explicitly gives us back the 3-point MHV amplitude with all of the delta Z bars included. So at the end, even though these leaf amplitudes are sort of non-singular and then it's sort of they only capture the scattering that occurs on a particular hyperbolic slice of spacetime, we can still combine them to sort of indirectly extract these distributional translation invariant scattering amplitudes. Yeah. And what's nice at the end, we can also sort of show that we can actually sort of come up with a 2D CFT that contains operators whose correlation functions compute these leaf amplitudes in a particular sort of semi-classical large N limit.
Maybe there's some connection to be made where the leaf amplitudes themselves can emerge from some slightly simpler Carolean limits, slightly less singular Carolean limits of ADS4 amplitudes. And then when you combine them together, you get the delta function, because there's some very interesting contour integral manipulations that you have to do.
Yes.
And I was in talks by Akshay and Rama, and the same kind of manipulations they have to do to take the flat space limit of the ADS4 amplitude. So there might be something interesting there.
What are the two things on the drawings that are canceled?
I don't think there were two things. When you combine the leaf amplitudes together, you get the sine pi beta time. Like after you cancel, you get a one single thing times the sine pi beta. So they have that thing, but where the sine pi beta is replaced by something that's regulated by the ADS length scale, so to speak. And when you take that to 0, they just land on the final expression. But to show that it's the correct flat space amplitude, they have to do the same contour manipulations that we have to do.
Yeah.
So,
I mean,
to show that sine pi beta gives some non-zero and delta function singularity.
I mean, you could presumably could relate sort of the integral over Klein space or Minkowski space to some limit of like a flat space Witten diagram if you did it correctly. So there might be some way to manipulate their formula into some expression where you could separate out in this way and get these two terms to cancel.
There might be some foliation of
Yeah.
ADS4 that nicely lands onto the foliation of ADS3 foliation of flat space.
Yeah, I mean, certainly like ADS4, I think you can also foliate, or you can foliate ADS spacetimes with a similar foliation, except where I think now there's sort of constant time slices.
Right.
So it's a bit different, but there's probably some way to land on this type of a formula like this from a flat space limit of ADS.
It would be interesting to see what that is. Yeah.
Yes.
Walker, I know you set it up in 2-2 signature, but just this trick of regularizing a delta function by saying it's that principal value prescription, that could be done in any signature.
Yes.
The only thing is it looks like here it's somehow coming from an I epsilon regularization of a Feynman propagator, right? This is P1 plus P2 squared in the denominator regularized with this Feynman I epsilon. How tight, and that's, this difference of I epsilon prescriptions is correct in 2-2 signature. how tied to 2-2 signature are you really? Suppose I don't care
here-
about leaves, suppose I don't care about ADS foliations, I just want to regularize the delta functions in this way.
Yeah, I think since our goal here was to try to explicitly get out this distributional 3-point function, we want to work in 2-2 because in 3-1 signature, right? So the z's and z bars or
Yeah,
sigmas and
but
sigma
you're
bars
going to
have-
use the same trick to get rid of delta
Comp-
functions in
yeah.
endpoint functions.
I mean, in particular, we could these integrals, at least certainly at higher points, we can do in 3-1 as well. The two simplifications we wanted to match this 3-point distributional amplitude, which is non-zero only in 2-2, and also because we were in 2-2, both the time-like and space-like regions are foliated by Lorentzian ADS 3 mod z. Well, in 3-1 it would be Euclidean ADS 3 or Lorentzian de Sitter 3. And so one might worry that getting the de Sitter answer from the ADS answer might be slightly more complicated than just flipping all the sigma bars to minus sigma bars, which here is just a change of coordinates. That's completely well defined. But again, here it's all convenience, really. We could do this in 3-1 as well.
Wouldn't it be just an analytic continuation of the?
Yeah, presumably you could relate it to some analytic.
But it looks like
analytic answer.
I could try to compute it in 3-1, an endpoint amplitude, where instead of using the Feynman I epsilon prescription for my propagators, I pretend to be in 3-1, but I use this difference of I epsilon prescriptions for my propagators. And that would lead to the same regular, if I just keep track of each of the terms separately, that would lead to the same regularized delta functions.
Yeah, I mean, again, it should also work. It's here. Yeah. And again, like particularly the I epsilon prescription here did come out of our computation. Ultimately, when I define the leaf amplitudes here, I need to put in an I epsilon prescription to regulate the omega integral, which becomes an I epsilon prescription in this bulk to boundary propagator. And that follows through all the way to these very particular choice of I epsilon prescriptions. And again, you could do all of this in 3-1 as we did it in 2-2 for convenience. And because we wanted to match the
But it's the correct I epsilon prescription in
Yes.
2-2, and it would be an incorrect I epsilon prescription in 3-1.
Yes. Mm-hmm. But in this case, this is at least the answer that will give us the distributional 3-point function. But they also did that with massive amplitudes as well, and there's something a bit, and that has some other challenges, I think. Okay. I think the one other thing we were able to show is we're able to show that if I defined a simple 2D action, so I'm going to take the action to be equal to 1/8 pi. So I'm going to start with some large number of free fermions. Yeah, psi j, d bar, psi j. I'm going to take a single weight -3/2 fermion eta. So this action here is rho d bar eta, and here h of eta, h bar of eta is equal to -3/2 0. And then finally, I'm going to take Liouville theory. So the actual whose action on a plane is d squared z. What we were able to show is that if I take this theory, which is normal 2D CFT, which is a large number of weight 1/2 free fermions, and then just a single weight -3/2 fermions whose role is going to be to give us our negative velocity gluon and sort of project us into the MHV sector by requiring us to have exactly 2 negative velocity gluons, and then finding Liouville sector, the Liouville theory. What you can show is that, so the spectrum of Liouville theory has these vertex operators of definite momenta. So they take the form, sort of VB times sigma. In particular, if this momenta here is proportional to B and the B goes to 0 limit, these basically just sample the value of a cosmic field. So I could define a positively gluon operator that is equal to some, and what we have here is the positivity is equal to a normalization constant times a normal order product of psi I, psi, or yes, okay. Shit, I misplaced my notes. Yes, basically just the psi j, and where my negative velocity gluon operator is equal to some other thing times now eta d eta psi d psi times v of b, and this is now delta -1/2. We were able to show exactly that if I take the limit where b goes to 0 of some correlation function of some two negativity of these gluon operators, and then some number of positivistic gluon operators, that the resulting correlation function is exactly proportional, is exactly equal to our leaf amplitude at endpoints. So I can calculate my leaf amplitude using this sort of 2D CFT in a large and semi-classical limit, and then sort of plug this into our dictionary relating the leaf amplitudes to our celestial amplitudes, and ultimately obtain a sort of distributional 3-point function sort of indirectly from this 2D CFT. Yeah. Yes, so in particular, though, these fermions here, we used to sort of form a level 1 Kac-Moody algebra for SON, and they gave us just the trace of TA1 to TAN part of it. Then we have to sum over the color orderings from that. These eta d etas give us the Z12 to the 4th in the MHV amplitude, and because eta has a weight -3/2, eta has sort of 4 globally holomorphic 0 modes on the sphere. So any correlation function to be that's non-zero has to have exactly 4 insertions of eta, and because each negligity gluon has 2 etas, you can only have exactly 2 negligity gluons. And so the only non-zero correlation of these operators have exactly 2 negligity gluons and any number of positivity gluons. And in this large n, large central charge limit, they give us exactly the leaf amplitudes. Where the Liouville theory gives us the integral over ADS3, and these fermion systems just gives us the MHV prefactor.
Of course, infinitely many other operators in this CFT.
Yes. So here we're only claiming that these operators reproduce it. Presumably, for example, one could look at, say, just the undressed Liouville operator, and one might be tempted to relate this to try to match up with some splitting function in the bulk and try to see what it would be dual to, and you can at least sort of looks like it would be dual to 4th order scalar, whose Cantor term was phi box squared phi trace S squared interaction, and you can match up that splitting function at least.
But that was going the either way. I could also have loads and loads of fermions with lots and lots of derivatives to make sure it doesn't vanish, and then I could have an arbitrarily complicated representation of the gauge group.
Mm-hmm.
And all of those states are there in this CFT.
Yes, I mean, again,
Okay, a large enough K or no. There's more trivial and annoying, so let's put it that way.
now, at this point, we've claimed only that these operators replicate the leaf amplitudes. We haven't made a claim about what other operators in this theory would be dual to. And one would be tempted to try to identify them other bulk fields, but that's the interpretation of them is less clear. Mm-hmm.
Yeah.
Mm-hmm.
Yeah.
Yes. Mm-hmm. Yes. Mm-hmm. Yeah. I mean, that's all we've claimed. Mm-hmm. Yes. I mean, here was more of a proof of concept. We want to claim that this sector of the CFT replicates this other sector, this sector of the scattering amplitudes. But again, there's other scattering amplitudes that this doesn't replicate because we projected us into the MHV sector with the eta system. And conversely, we haven't provided a bulk interpretation for other 2D operators.
Yeah, related to that, is it really an equality in the sense that how do these operators know that they only scatter in MHV amplitudes?
Well, so what we're saying is that these operators, this is an equality. We've chosen the normalizations here, so that this is the case. How it works is that, again, you can show that these just generate the MHV prefactor, the fermions, and then
Sure.
the correlation functions of the Liouville theory in the semi-classical limit where b goes to 0 strictly, and all of the operators are light, they replicate exactly a scalar contact Witten diagram.
And what I mean is the left-hand side cannot be any gluon operators, right? Those are only the ones who scatter, whose non-zero correlation functions are in.
Yes. So again, like if I inserted like a third negative gluon or 1, that the correlation function would be 0. Obviously, the amplitude that we would match wouldn't be 0, but we've only done this for the MHV sector. Beyond the MHV sector, it becomes more complicated because we can no longer treat the scattering amplitude as a local interaction in the bulk.
And also, so suppose I just look at a 3-point function, but I don't take the limit of B going to 0.
Yes. Mhm.
So the Neuville correlation function is known. It's this DOZZ formula. Does that correspond to anything interesting on the amplitude side? Pick
that-
exactly these operators with exactly the representations you've chosen, just 2 minus 1 plus or something, but don't take B goes to 0.
I would say this is very speculative. One would be tempted to try to match this with some type of loop correction.
There's no loop correction to the 3-point amplitude.
Yes. Well, I know certainly Taylor and one of his followers has claimed that if you do this, he doesn't get translation invariance back, but he claims you can match some parts of the running of the coupling constant in Yang-Mills from the 3-point Liouville amplitude. Although there's a lot of terms that he has to a way to get there. So I don't like to speculate about that, but this is against I don't really have much more to say about that now. Here our goal is to sort of explicitly cook up the example with translation invariance, and then that's certainly something we'd be interested in looking at. No. Okay, so here certainly we suggested that I can take sort of linear combinations of two CFT correlators and end up with a translation invariant result, even if the actual CFT itself doesn't have the symmetry. And so in the last 20 or so minutes, I'm just going to quickly describe an example where we can quantize the scale of field theory in Klein space in a way that sort of makes a similar thing manifest, where I define some quantum system that has no translation invariant states, but in a tensor product of two Hilbert spaces, I can identify a translation invariant state. Okay. And so to do this, we're going to consider a space whose metric is given by ds squared equals to e to the 2, what I'm going to call iota, because I'm running out of letters. And this metric is going to be equal to, yes, I want to have, yeah, it's going to be equal to minus e to the 2 iota. And sorry, this is ds squared equals minus e to the 2. Let's just call this okay, I'm just going to call this a t for now. Of dt squared, I have plus, ds3 squared. Yes. Well, this is now a metric on EADS, ADS3. Now, basically what recognizes this as sort of this is a metric just on the time-like region of Klein space, where I'm treating where e to the iota is simply equal to x squared in Klein space. Right, and so this is here I'm going to write this as being equal to plus hij dxi d. So I'm going to consider a theory whose action is going to simply be d3x, where this is a metric where these are the coordinates on ADS3, and then d iota, I have the root g, and then let's take minus g mu nu, d mu phi, d nu phi. In particular, starting from this action, which is again going to be defined inside the interior of the time-like region of Klein space, I'm going to quantize this theory by defining my momentum operator to be pi of x equal to delta s by delta, now d iota phi, sorry, dt phi. Where here, again, t is this coordinate that's labeling which of these ADS slices I'm on. And we can find, in terms of use, that the Hamiltonian takes a particularly simple form. So the Hamiltonian here is now equal to the integral of d3x with pi squared divided by 2e to the 2t, then the root determinant square root of the determinant of my metric on the ADS slice plus e to the 2t. Again, metric j over 2 I phi dj phi. So when I do this here, now I can promote my momenta and position to operators, and I'm going to define it so that my field operator phi operator is going to label t and x hat, and this canonical momentum that's conjugate to little t phi at the same t x hat prime is simply going to be the delta function 3 of x hat minus x hat prime in the familiar way. And now we can define a state, perhaps. And now these are sort of, again, a canonical conjugate pair. Now, because I've effectively chosen to quantize by treating the Hamiltonian as my dilation generator in Klein space, this is going to define a different Hilbert space than the familiar, just say choose a time and treat your Hamiltonian as d by dt. But we can still sort of make this work out, and I can define a set of states that say it's that diagonal, say phi at some time t of x hat. So I'm going to define this state to be t, so I'm going to define this state phi of xt that diagonalizes so that this is equal to phi of x t. Now in particular, by running through this sort of familiar skeletonization argument, I can show that with this definition, that if I take the overlap between, say, some phi of x at some time tf with some phi of x at some time t initial, I can show that this is actually equal to the path integral where I integrate over all fields phi of e to the minus d for x of just my normal, d mu phi, but where I in particular I restrict that phi of tau equals e to the t x is equal to phi. Let's call this phi I. So here, if I look at this in terms of Klein space, I've given some fixed data on this slice here. I've given some other fixed data on the slice here, and I've calculated the overlap between these two states by doing this path integral over the region of the interior. Now I can also do something pretty similar where I instead do this in the space-like region instead. So I can, again, I choose some coordinates in the space-like region of Klein space so that x squared is equal to e to the 2t. I choose effectively my Hamiltonian to be the generator of shifts in t so that it generates dilations in the bulk. And I can similarly define a system where, again, I give some data here on some tau t initial. I give data on some t final. These again are labeling these constant x squared slices, and then do the path integral over the interior, and that will calculate the overlap between, again, the states phi I, ti, and phi f, tf. Okay. And so again, each of these systems on their own, because I've chosen this foliation of space-time, don't have any state that's translation invariant on their own. However, in particular now that I have these two systems, I can define the state in particular now. So, right, so our coordinatization is going to take, so in particular now let's consider the state where I take this slice here and I push it towards the light cone. So I can always do this by sort of sending my ADS to radius to 0 while sending my point on ADS to the boundary. And so I can define a state now where the limit, say, of my point goes to the light cone from the time-like region of some phi. Actually, it's going to be easiest. So our coordinatization is going to be the x hat mu is equal to e to the t, and that, okay, I'm just going to define this. Sorry, I just didn't quite print out correctly. Okay, basically, simply by taking the limit where my t approaches either minus infinity, that pushes my surface to the light cone where I define data. So I can define a state in each Hilbert space where I have some fixed data on the light cone itself. And so in particular in the time-like region, this defines some state, let's call this phi light cone in the time-like region. I can define a similar state in the space-like region by giving data on this slice instead and pushing that to the light cone. And this defines another state, say phi light cone in the space-like region. And in particular, I'm going to define a state that's given by 0k, and it's going to be equal to a path integral over all of these functions on the light cone itself of just phi light cone in the time-like region, then phi light cone in the space-like region. And in particular, I'm going to claim that this state is translation invariant. And in particular, to show that we can simply write out what this state actually calculates from a path integral point of view. For example, to say if I, let's say if I define some state on the system where I give some data, say up here, and I separately give some data over here. So I have, say, phi boundary time-like, phi boundary space-like. And if I take now the overlap between phi boundary time-like, phi boundary space-like with my state 0k, right? This is now going to be my path integral phi L of phi boundary with phi L, phi boundary now with phi L. And this is in the space-like region, this is in the time-like region. And in particular now, right, this is going to become the integral over fields in the time-like region. With the boundary condition that phi restricted to the light cone is equal to phi L of e to the minus s. This is going to become the boundary condition, and that phi of tau goes to infinity is equal to phi b. This is, again, give the condition that phi restricted to the light cone is equal to phi L. And then I have some other boundary condition at tau. This goes to, again, e to the minus s. And then finally, I have the integral over d phi L. And so putting this all together, this simply computes an integral, because I'm basically just integrating over everything with fixed boundary conditions on the light cone, and then integrating over this boundary conditions on the light cone. This is calculating a path integral where I simply fix the data on the 2-2 equivalent of scry to be some fixed thing. And because this action is translation invariant, this state itself is translation invariant as well. And so even though these time-like or space-like Hilbert spaces are defined by quantizing with respect to these constant x-squared surfaces, each of these Hilbert spaces contains no translation invariant states independently. There is a translation invariant state in the tensor product of these two Hilbert spaces as well. So in some sense, we could, in this context, we could say that translation invariance emerges from entanglement between these two systems. And in fact, this is a maximally entangled state, so the trace of this state is simply the identity, which is because these are simply entangled by the requirement that the fields are always continuous in the interior. And in particular, while this sort of feels like an artificial example where I've chosen a very unusual way to quantize the system, it may not be perhaps so unusual. For example, one thing you can try to do is you could try to take client space, take your action on client space and try to reduce it to an action on ADS3. This is in general, and then try to apply the ADS3 CFD2 dictionary to that action. However, if I work with this action, and in particular, I do this, say I take my action, I try to reduce it to this single ADS3 slice. But the sense of time on this ADS3 slice is actually an angular variable in client space, and so it differs from just the sort of choosing some set of time in the bulk and quantizing in that direction. And so if I try to actually use it to obtain an action on ADS3 and then quantize it as I would any normal action on anti-de Sitter space, I'm choosing a sort of unusual quantization. And in particular, I need to do this in both the time-like and space-like regions. And so I could define one Hilbert space in the time-like region by quantizing with respect to ADS time, a similar Hilbert space in the space-like region by quantizing with respect to ADS time in the space-like region. And then I need to sort of put in more information to figure out what the actual state of the system should be. And that information is continuity on the light cone. And again, this should entangle these two systems in a similar way by requiring that the fields be continuous everywhere. And so again, in this case, you could hopefully try to obtain some translation invariant state in the tensor product of these two ADS actions, even though each ADS isn't translation invariant. Is there any questions? This is what I had prepared.
Questions? Could you explain again how you restore the translation invariant Hilbert by combining the two Hilbert spaces on the two?
So again, so basically the idea is we're going to try to quantize a scalar field in a slightly more natural way. Now, in Klein space, because I can rotate any of the time-like directions in any other time-like direction, there isn't a separated like future pointing and past pointing light cone. And so if I just choose some direction of time, I'm breaking Lorentz invariance. And so our idea was to try to quantize the theory in a way that would preserve Lorentz invariance, but break translation invariance. So effectively, I can think of, instead of just taking my time direction to be equal to just say x naught, I can choose basically to treat time evolution as giving evolution along these sort of constant ADS3 slices. And I can define a Hamiltonian that now generates translations. If I specify data on this system or a state here, I can use the dilation generator to map it to some state with, say, definite field value here instead. And I can write down some sort of almost canonically quantized system where this becomes manifest. And so in particular, in this system, if I define some state with fixed field value along this light, and another state with fixed field value on this slice, the overlap between these two states, which can be something like phi f, tau f, overlap phi I, tau I, where these are defined by diagonalizing the field variables now on a particular ADS slice, then the overlap between this state is calculated by doing the path integral between these two slices of Klein space with Dirichlet boundary conditions for the fields on these two slices. I can now define a similar system in this region where I can give data on this slice here for some other tau initial, some other data on this slice, and calculate a similar overlap between phi I, tau I, and phi f, tau f. But in the limit, in particular, I can take the limit where tau I goes to 0. So I give data on the limiting value of the light cone as this slice approaches the light cone. I can do it similarly in here. So that sort of sews up this region. And then integrating over what data is on the light cone is basically just imposing the constraint that the field is continuous here. And then I can push this overlap to scribe by sending tau to infinity instead. And you can see that ultimately this state is calculating the overlap between that ultimately this combination of states is calculating some path integral, which is Dirichlet boundary conditions on scry itself, and with the fields being continuous everywhere in the interior. And that sort of is now obviously translation invariant.
So from MHV diagrams, we know that MHV tree amplitudes happen at local interactions in space. And since they're local, they live on some leaf. And so in some sense, it's not too surprising that for a leaf theory, you can get an MHV amplitude. It's impressive to do it, but it's the easy one.
Yes.
Beyond, as soon as you go to NMHV or anything beyond that, that's no longer true, right? They're going to live at different points in space-time, which won't necessarily be on the same leaf. I think in your theory, if you put 3 negative helicity gluon operators and arbitrary, you just immediately get 0 because of the.
Yes.
If I change the statistics of your eta field, so they've got precisely 6 0 modes, so that you don't just trivially get 0.
Yes.
I could imagine that what that is a part of an NMHV amplitude where both vertices are sort of artificially constrained to lie on the same leaf rather than just in general. Do you know if that is what you get, or whether you just get, well, yeah. Do you know anything about what you get if you do that?
Unfortunately, no. One might be tempted to speculate that you could get something like a trace of B cubed form factor or something like this. Or at least something that would be related to a 3 gluon magnificent amplitude, but we haven't actually computed that. It's been a while trying to find a sort of similar decomposition of the NMHV amplitude where we start out with some like MHV rules formula and then try to decompose that into an integral over Klein space over 2 points in Klein space and separate that integral into some type of leafy decomposition. But
Wait, I suppose
never
the interesting thing would be whether you get something that's really like a trace of B cubed, i.e. where you've got 2 MHV vertices, but they're sitting right on top of each other, or whether you can still have 2 MHV vertices that are separate, but on the same leaf. The latter would be much more interesting.
it would be more interesting, but unfortunately, I can't say anything concrete about that. So again, you can try to play around with various like split representations of bulk-to-bulk propagators to try to maybe push some MHV life formula onto some leafy decomposition, where you integrate over the weight of the exchange field, but we hadn't gotten it to actually work out in a nice concrete way yet. So. Mm-hmm.
All right, I don't see any more questions. So thank you very much, Volker, for the nice talk.